So I'm going to go ahead and get started. Let me pull up the camera. Okay, so today we're going to finally talk about Cauchy's theorem and the Cauchy integral formula. Um, there's a couple of sections on complex line integrals, fundamental theorem of calculus for complex integrals and so on. So I'm just going to kind of speed through that first. Most of it is just analogous to the real case. So, complex line integral is exactly what it sounds like. I mean, you have some integral over some curve, and all you're doing is computing the line integral exactly as you would in R2 along some curve. So, for example, you could compute the integral from 0 to 1 plus I c squared dz, where by this I mean along the straight line, the straight line segment from z equals 0 to z equals 1 plus I. Oh, switch pens here. So here's 0, here's 1 plus I. We're computing the line integral along this curve. Well, we can parameterize that curve pretty easily. This is just the curve t times 1 plus I, where t is ranging from 0 to 1. And the differential dz is just 1 plus I dt. And so we have that the integral is the integral from 0 to 1 of t squared 1 plus I squared times another 1 plus I dt. And this comes out to, so this is now just your usual real integral, which we can certainly take care of. And this comes out to 1 plus I cubed over 3. So exactly like the real case, just parameterize your curve and then do the integral. Okay, so here is a more important example that we'll come back to, which is the integral over the closed curve modulus of z equals 1. That's a circle of radius 1 centered at the origin. So a point, well, let's call this theta and take this point here. This point can be parameterized by the exponential. I just wrote the theta in the wrong place. Wow. Theta. Anyway, so any point along this circle can be written as e to the I theta. Right? So what this really is the integral from 0 to 2 pi of, so 1 over z, that's e to the minus I theta, and then dz, so here z is e to the I theta, dz is I e to the I theta d theta. And so we have an I e to the I theta d theta. This is the integral from 0 to 2 pi of I d theta, which of course is 2 pi I. Okay, so this result, I'm going to write down again and put it in a box so that we can come back to it later. Okay. So more generally, we have the following. So if we integrate z minus z naught to the nth power for some z naught in the complex plane, which is fixed, if we integrate that around the circle centered at z naught, radius r, then this will come out to 0 when m is not -1, and it'll be 2 pi I when m is -1. So when m is -1, this looks like this. Okay, so that's an important point. So let's go ahead and show that. So we can parameterize that as z naught plus r e to the I theta, right? So we have our complex plane, and we have some point z naught over here, and we have a circle of radius r, then a point on the circle is written as z naught plus r e to the I theta. Okay, so we can plug this in, and what we find is that our integral, let me just call it I, so we don't have to write it again, is the integral from 0 to 2 pi of I r to the m plus 1 e to the m I theta plus another I theta from our differential d theta, right? Yeah, we just double check that here. This is r times I e to the I theta d theta. Yes, okay. Okay, so again, this integral is not hard to do. This is I r to the m plus 1, the integral from 0 to 2 pi of e to the m plus 1 I theta, d theta. And so when m is not equal to -1, so let's do this in two cases. When m is not equal to -1, so that this coefficient or this exponent is non-zero, then what we find is that the antiderivative is going to give us r to the m plus 1 over m plus 1 I e to the m plus 1 I theta, where we evaluate theta from 0 to 2 pi. But when m is equal to -1, suddenly this exponential is just equal to 1. And what we find is that the integral evaluates to 2 pi I. So this becomes 2 pi I. I lost my, yeah. Okay, so when m is -1, the r's go away, right? This also becomes 1. Okay, sorry, I thought I was missing my r's, but we're good. So we evaluate this guy at 2 pi and 0, and we remember our Euler formula. Both of these guys will evaluate to 0. And so what we're left with is 0 in the case that m is not -1, and 2 pi I in the case that m is equal to -1. Okay, so this is another one to keep in mind that we will come back to. All right. So let's note, just as in the real case, we can make an estimate of the following form. So this just follows from the Riemann sum definition of these intervals. So if we have that h is bounded above by m, and gamma has length L, so the curve that the integral is along has length L, then what we find is that the magnitude of our integral is bounded above by ml. Okay. So this estimate is going to be used a lot. I mean, it's not really anything new, right? We use that kind of thing in real analysis all the time. Real analysis all the time. Something else that is not really new is the fundamental theorem of calculus. It still holds for analytic functions. So if we have so if f is a continuous function on a domain D, then a function f of z, sorry, capital F of z on D is a complex primitive for lowercase f if uppercase f is analytic and its derivative is lowercase f. Okay, so that's just a definition. And then the usual fundamental theorem of calculus still holds. So if f is continuous on D, and if capital F is a primitive for lowercase f, then the integral from a to b, f of z dz is f capital F of b minus capital F of a, where we should note that the integral can be taken over any path from a to b. Okay. Not really. Let's let's get that proof, but it's short and sweet. So it's in the book if you want to see it. But the point is just that this theorem still holds in complex analysis for analytic functions. And so that allows us to do very simple evaluations that we're used to, like the integral from 0 to 1 plus I of z squared dz, which we've already seen. But now we can use the usual fundamental theorem of calculus. We know z cubed over 3 is a primitive for z squared. And so what we have is that this is 1 plus I cubed over 3. Okay, so great. We can use this thing that we're used to. The other version of the fundamental theorem of calculus also still holds in a in your usual first course in calculus. You see it written as a part 1 and a part 2. This is the part 2. Okay, so let f be some analytic function on a star-shaped domain, then f has a primitive on D, and it is unique up to an additive constant. And it's given explicitly by the integral from z naught to z f of zeta d zeta for z and d. So z naught here is some fixed point, fixed point in d. So the the uniqueness up to the additive constant comes down to this choice of z naught here. Okay. All right. So a lot of the usual things from ordinary real calculus still hold, and that's all these last few sheets were saying. And now I want to move on to something new, which is Cauchy's theorem. So let f of z equal u plus iv. Then we have that f of z dz is u plus iv times, we can write the differential in the same sort of way, split it into a real and imaginary part. And multiplying these guys out, this is u plus iv dx plus minus v plus iu dy. So we find that f of z dz is a closed differential exactly when the y derivative, u plus iv, is equal to the x derivative of minus v plus iu. We derived this condition in an earlier lecture. If we take the real and imaginary parts, we have du by dy is minus dv by dx, and dv by dy is du by dx. But these, remember, are the Cauchy-Riemann equations. And remember, the Cauchy-Riemann equations are a condition that is equivalent, more or less, to analyticity. So we have the following theorem. A continuously differentiable function f on D is analytic if and only if the differential f of z dz is closed. Okay. All right, so that's just one small result that, well, I don't know if I should say small, but it's a result that will make the following possible. So here's Cauchy's theorem. We let D be a bounded domain with piecewise smooth boundary if f of z is an analytic function on D that extends smoothly to the boundary, then the integral along that boundary, so the boundary is a closed curve, is exactly equal to 0. Okay, so what does that say? If I give you some bounded domain, and you try to integrate f along the boundary of that domain, well, if f is analytic inside that domain, then in fact the integral is going to be 0. So here's our proof. So the integral along the boundary we can write as the integral along the boundary of u plus iv dx plus minus v plus iu dy. So this is the form of f of z dz that we wrote earlier. Now, since f satisfies the Cauchy-Riemann equations, so remember f is analytic by assumption, and analytic functions satisfy the Cauchy-Riemann equations. So since they satisfy the Cauchy, so since f satisfies the Cauchy-Riemann equations, we have from Green's theorem that the integral over the boundary of the y derivative of so the guy in front of the x differential minus the x derivative of the guy in front of the y differential. We're integrating over this two-dimensional domain now. Well, this is going to be equal to 0 by the Cauchy-Riemann equations. Why? Because the Cauchy-Riemann equations tell us that this integrand is exactly 0. Okay. So that's it. That's the entire proof. But the result itself is very nice. I take, for example, the domain modulus of z between little r and big R. So this looks like an annulus. So let's take a point. This is 0, and we have a circle of radius little r, and then another circle of radius big R, bigger than little r. Our domain is that region in between. Okay, so if f is analytic, on D, then what does that tell us? That tells us that the integral over the boundary of D, this is equal to 0. So I'm writing it on the left because I'm also going to write this another way. This is equal to the integral. So let's remember the convention that we chose when we were talking about line integrals. We said that we were going to choose the convention so that when you're traveling along this curve, the domain that this is a boundary of is going to be on the left, right? And so down here, if I'm traveling along this curve, I want the domain to be on the left, and so I need this guy to point that way. So the boundary is the union of these two curves. So the curve, so the integral along the larger circle looks like this. And now the integral along the smaller circle, well, we're going clockwise here. And when we go clockwise, we pick up a minus sign. Okay. Maybe I should explain that minus sign a little more here. So we can think about this circle as also bounding this region, this disk on the inside here, right? And so the integral along the boundary of that disk is the integral along this circle, right? And so the proper form for that integral would be in this direction, going with that counterclockwise. When we go in the opposite direction, well, it's like flipping the like in the usual real case, it's like flipping these bounds. And so we pick up this minus sign because we're going in the opposite direction. Okay, so combining these two results, that tells us that the integral over the bigger circle is actually going to be equivalent to the integral over the smaller circle. Okay, and little r, big R, these guys were chosen arbitrarily. So this is just always true as long as we have a nice enough domain, right? We need f to be analytic inside this domain, and well, that's really it. The boundary needs to behave nicely. That's pretty much it. Okay. So here is a nice example. Let's compute 1 over the square root of 2 pi times the integral from minus infinity to infinity of the Gaussian times a complex exponential, which you might recognize as the Fourier transform of the Gaussian. And this should be, in fact, a Gaussian. So this is for t between minus infinity and infinity. And what we're going to do is, so we want to compute this real integral, right? And now we're going to do a very, very common trick in complex analysis, or at least in the integral calculus, which is to write a contour which sort of includes this integral in it, but close it. So we'll go from minus r to r like this. And then in a moment, we're going to let r approach infinity. But in order to use Cauchy's theorem, we need to complete this curve. We got to close it. So we'll go up and we'll make a rectangle. We'll go to, this is r plus it. And then we'll come across to minus r plus it. And then we'll come down. Okay. So this entire rectangle is certainly a closed curve bounding this region inside of it. Right? And well, two exponentials here. Exponentials are very well behaved. These guys are going to be analytic on the inside of this rectangle. And so that tells us that, so if we call this whole thing gamma, the integral along gamma of the Gaussian times the complex exponential should be equal to 0. So that's what Cauchy's theorem guarantees us. But remember that we can write that integral as, so we have 0 equals, I'm going to move this 1 over 2 pi all the way out. So this is equivalent to the integral from minus r to r of, sorry, I should replace these with z's just to be clear. So I'm replacing my x's with z's here to be clear that I'm integrating over a complex variable, right? So I've exchanged this real integral for a complex integral along this boundary. But that complex integral consists of the integral from minus r to r of, and now I can parameterize z. So along the real axis here, the imaginary part is 0. So I can feel free to write this as e to the minus x squared over 2, e to the minus I t x dx plus, and now I need the integral from r to r plus it along this vertical line. Well, we can parameterize that as follows. We can write z equals r plus iy and let y go from 0 to t. Then dz is I dy. And so now we're going from 0 to t, and this becomes e to the minus r plus iy squared, e to the minus it r plus iy, and now dz is I dy. Now I go this way. This is an integral, and now I'm going to parameterize z equals x plus it, where x is ranging from minus r to r. And now dz here is dx. And I'm integrating from r to minus r. Okay, so that's x plus it squared over 2 e to the minus it x plus it dx. And then finally, I have this curve going downward. And I'll use the same parameterization as over here, but now, well, sorry, with a minus sign here. So I'll make this a minus r. And now I'm going from t to 0. So that's e to the minus, and now it's minus r plus iy squared over 2, e to the minus it minus r plus iy dy, and I need an I. Okay, so let me just recap really quick. So we have this real integral we want to compute. And so what we do is we replace that real integral with this complex one, and we close the contour. So the contour includes the original integral we wanted once we take the limit to infinity, plus these other ones that just close it so that we can use Cauchy's theorem. And so now the way we're going to compute this integral is by noticing that it appears here, right? And then evaluating each of these integrals. But as r approaches infinity, something nice happens. What we have is, well, the first integral becomes the one we want. So we have 0 equals 1 over root 2 pi, integral from minus infinity to infinity, e to the minus x squared over 2, e to the minus I tx dx. That's the guy we want. And what happens to the second guy here? Well, we have a complex number I here being multiplied by r. So this thing is going to oscillate in r. But over here, we have an r squared with a minus sign in front of it. That thing is going to go to 0 very fast, right? And in fact, the entire integral is going to approach 0 as r goes to infinity. So this thing is going to go to 0 as r goes to infinity. And same thing down here, right? We're going to have an r squared here when we square this whole thing with a minus sign in front of it. That thing is going to go to 0 as r goes to infinity. And so we're left with the integral we want plus the integral from infinity to minus infinity of e to the minus x plus it squared over 2, e to the minus it x plus it dx. Okay, so I'm going to swap the ordering here to pick up a minus sign and then add it back over to the other side. So now what we have is that the integral we want is equivalent to, I dropped my 1 over 2 pi, 1 over root 2 pi. The integral from minus infinity to infinity of e to the minus x plus it squared over 2 e to the minus it x plus it dx. And this integral we can write, so if you expand the square out, multiply everything out here, what you'll find is that this is equivalent to 1 over root 2 pi e to the minus t squared over 2 minus infinity to infinity x plus 2it squared over 2 dx. And now we use this result that the integral from minus infinity to infinity of e to the minus, so basically a shifted Gaussian, right, is the square root of 2 pi over 2 here. We use that here so that this is equal to the square root of 2 pi, and what we're left with is e to the minus t squared over 2. And that's exactly what we wanted to show. Okay, so there are other ways we could have solved this integral, right? This is not the simplest one. This is just to showcase how this method usually goes. What you do is you have this real integral you want to compute. You write down a contour which includes the curve that you're trying to integrate over, and then you close that contour. And if your function that you're trying to integrate is analytic inside of that contour, well, then you know the integral along the entire curve is 0. And so that allows you to write the integral you want as the sum of the remaining parts, the sum of the integrals along the remaining part of the boundary. And a lot of the time, when you let the bounds of your contour go to infinity, a lot of the time those other integrals go to 0. Okay. So what does this tell us, by the way? So remember, this integral we can recognize as the Fourier transform of the Gaussian. And on the other end of this, what we're finding is that this Fourier transform is still just a Gaussian. Right? And so this tells us that the Gaussian is an eigenfunction for the Fourier transform operator with eigenvalue 1. But we don't have to stop there, actually. We can define the Hermite polynomials. And Gamelin calls them the Hermite orthogonal functions. So the Hermite polynomials will be Hn, and the Hermite orthogonal functions will be phi n. So the Hermite polynomials will be minus 1 to the n, e to the x squared, times the nth derivative of the Gaussian. And the Hermite orthogonal functions will be the Gaussian times the Hermite polynomials. Okay. And what we can do is, well, first of all, well, let me verify, do I actually need this? I believe I will use this fact. Yeah, okay. So what we can do is we can show that Hn is a polynomial of degree n that is even when n is even and odd when n is odd. I'm not sure if we're going to use this even and odd fact, actually, but I'll use the fact that this is, in fact, a polynomial. And the way we see this is by applying the Fadde-Bruno formula, which just tells us how to differentiate composition of functions n times. It tells us that this is the sum from, well, over all n tuples that satisfy this equation. Um, I wrote down a level of detail I don't really need in my notes, times some constant, which depends on these guys, times the derivative of the outside function, which is the exponential here, with the inside function plugged in. So it's a derivative to like the m1 plus m2 plus so on, all the way to the mth power, but this is an exponential, so it's not going to do anything. Times the product from j equals 1 to n of the jth derivative of the inside function. And that's to the mjth power. So this is the Fadde-Bruno formula. It's a nice one to know. I would maybe take a peek at it after this if you don't know it. And what we notice here is that this guy is 0 for j greater than 2. So then what we find is that this is equivalent to the sum over the same thing, the constants e to the minus x squared minus 2x to the m1 minus 2 to the m2 times, and then we have a bunch of zeros unless these exponents are equal to 0. So I'm going to write that as 0 to the m3 with the understanding that 0 to the 0 will mean 1. So this is in fact an integral, or it's not an integral, a sum over m1 plus 2m2 equals n. These constants, I'm going to stop writing this, times minus 2 to the m1 plus m2 times x to the m1, or the sum from, no, I skipped a step here. I'm missing e to the minus x squared. That's what it is from here. And so that tells me that my Hermite polynomials, let me pull the definition down here, are given by the sum minus 1 to the n plus m1 plus m2 x to the m1. And this guy, so one solution to this equation is when m2 is 0 and m1 is n, right? And that's the largest this thing can be, right? So yes, the degree of hn is in fact going to be equal to n. And so we're going to have a polynomial of degree n. And we see that when n is even, then m1 is n minus 2m2. And so we'll have an even minus an even, and so m1 will be even for all choices of m1. And so that tells me that this Hermite polynomial is going to be even. And when n is odd, so again, we have m1 equals n minus 2m2 from here. And so we'll have an odd minus an even, that's an odd number. And so all my choices of m1 will be odd. And so that tells me that my polynomial is going to be odd. Okay, so I really just need this fact that this thing is indeed a polynomial, I think. But this is a nice property that these polynomials satisfy. Okay, so in the last example, we showed that the Gaussian was an eigenfunction of the Fourier transform operator. And now I claim that, in fact, well, we have the following. So I claim that these Hermite orthogonal functions, let me pull the definition back up for you. Get these here. I claim that these Hermite orthogonal functions, which are basically a Gaussian times the Hermite polynomial, are also eigenfunctions of the Fourier transform operator. But their eigenvalues are no longer 1. Now their eigenvalues are minus I to the n. And in fact, we're going to prove this also by Cauchy's theorem. So we'll do the same thing. We'll introduce the same contour. So we have r plus it here, minus r plus it here. And we're going to travel along here, and then go up, and then go this way, and then go down like so. This is now a closed contour. Certainly a polynomial times the Gaussian is going to be analytic inside of this rectangle. And so we can go ahead and apply Cauchy's theorem to learn that so if we call this thing gamma, the integral along gamma is equal to 0. But this integral is equal to the integral from minus r to r phi n of x e to the minus I t x dx plus integral from 0 to t phi n. So I got to parameterize this guy again. This is r plus I y e to the minus I t r plus I y, and get an I and a dy, plus the integral from r to minus r of phi n of x plus it e to the minus it x plus it dx, plus, now we go down, this is the integral from t to 0 of phi n of, this one will be minus r plus iy e to the minus minus r plus iy. I get another I and a dy. Okay, so we let r approach infinity, and this first integral turns into the one that we want, right? So let's call this guy I. Okay. So we have that I is equivalent to minus the sum of these remaining integrals. And let's see what happens to a couple of these. So the ones along the vertical lines here. So remember, the Hermite orthogonal functions are defined as a Gaussian with this minus sign here, times this Hermite polynomial, which is indeed a polynomial, right? And so this Gaussian is going to dominate the asymptotic behavior with R, right? So since we have phi n of R plus Iy, for example, we're going to get an R squared term up here with a minus sign in front. And so this guy is going to go to 0 as R goes to infinity. And then the same thing is going to happen for this integral over here. We evaluate this guy at minus R plus Iy. And that's going to give me an R squared here with a minus sign in front of it. And so that's going to go to 0 asymptotically. And so what we find is that the integral that we want is equivalent to 1 over the square root of 2 pi. I'm going to swap the minus R and the R to get rid of the minus sign. And I'm going to let R go to infinity. Okay. So now I'm going to go ahead and write out exactly what phi n is. So I'm going to use my definition of phi n here. So this is going to be 1 over the square root of 2 pi times the integral, the integral from minus infinity to infinity of hn of x plus it e to the minus it plus x squared over 2 e to the minus it plus x dx. Okay, and we've already seen, or at least I told you in the previous example where well, the previous example was basically when n is equal to 0 here. But anyway, we saw that this thing in the integrand can be written as e to the minus t squared over 2, e to the minus x plus 2it squared over 2, just by completing the square argument. And this hn of x plus it is by definition minus 1 to the n e to the x plus it squared times the nth derivative of this Gaussian and I claim that this derivative, or these derivatives, I should say, with respect to x can be replaced by derivatives with respect to t at the cost of a 1 over I to the n. So this is certainly true when n is equal to 0. And now we're going to proceed by induction. So we have, so we're going to assume that it's true for n, and now we're going to show that it's true for n plus 1. Well, if it's true for n, then this is 1 over I to the n d by dx d n by dt n e to the minus x plus it squared. And we can exchange these derivatives with respect to different coordinates. But this is equal to 1 over I to the n, the nth derivative of minus 2x plus it e to the minus x plus it squared. And this is exactly what you would get. This guy is exactly the tth derivative of this Gaussian times 1 over I. Okay, so that proves the claim. And now I need to use this claim. This tells me that the integral I want, so I'll write it down again just so we have it here, is now equal to, so I'm going to use both of these results. So it's equal to this guy, and I'm going to use this result that allows me to write this in this form, and then I'm going to also use this result down here. Okay. So that tells me that this integral is equal to 1 over I to the n, e to the minus t squared over 2 over the square root of 2 pi, integral from minus infinity to infinity of minus 1 to the n. So I'm writing out my Hermite polynomial here, and I'm exchanging the x's, the x derivatives with t derivatives. I'm running out of space here. I need times e to the minus 2it plus x squared over 2 dx. Give myself more room. So this is 1 over I to the n minus 1 to the n, e to the minus t squared over 2 over the square root of 2 pi, the integral from minus infinity to infinity of let's see. Okay. So now I'm going to go ahead and expand this guy and that guy. And what I'll find is that combining those two things gives me e to the t squared, e to the x squared over 2, dn dtn, e to the minus x plus it squared dx. So again, that's combining this guy with that guy. And I can pull this guy out, doesn't depend on x, and I can also pull these derivatives out. And and that'll be the integral from minus infinity to infinity of this e to the x squared over 2, e to the minus x plus it squared dx. Okay. Um, okay. And now I want to expand this guy out. And what I'll find is that this is the nth derivative of e to the t squared times the integral from minus infinity to infinity, e to the minus x squared over 2, e to the minus 2itx dx. And this is the integral from the previous problem, which is e to the minus, well, actually, we have an extra factor of 2 here. So it'll be e to the minus 2t squared. And so that leaves me with, let me combine a bunch of things here. This will be e to the t squared over 2i to the nth derivative of e to the minus t squared, which is equal to, So plugging definitions back in, this will be equal to minus I to the n phi n of t. Okay, so that was a lot of trickery that went into using Cauchy's theorem to show that these e to the minus x squared over 2 times Hermite polynomial guys, so these phi n's, are eigenfunctions of the Fourier transform with eigenvalues minus I to the n. Okay, so this was actually an exercise in Gamma that has 2 more parts that I'm not going to do. The other 2 parts show that these eigenfunctions are in fact orthonormal. Okay, so let's see, how am I doing here? All right. So the last thing I want to do is tell you about Cauchy's integral formula, which is sort of distinct from Cauchy's integral theorem. And let me just say a couple of words first. Why would you want to know an integral representation of some function? And well, I think there are at least 2 good reasons. And one is you can use it to estimate the size of f. And 2, you can use it to obtain formulae for derivatives of f by differentiating under the integral sign. Okay, so with that in mind, here is Cauchy's integral formula. So assume D is nice, right? Bounded domain, piecewise smooth boundary, blah 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 blah. If f is analytic on D and f of z extends smoothly to the boundary of D, then we have that f of z can be written as 1 over 2 pi I times the integral over the boundary of D of f of w over w minus c dw. And this is for all z in the domain. Okay, here's the proof. So fix z and let epsilon be greater than 0. Let it be small. Consider the domain d epsilon, which is the original domain D, minus w minus c less than or equal to epsilon, minus this disk of radius epsilon, closed disk. Then, so what do we have here? We have some domain, might look goofy like that. And we have some point z, and we have a disk around z, radius epsilon, and we're removing this disk from the domain. So this is now d epsilon. So the boundary of d epsilon is the boundary of d, right? So this guy, union the boundary of this disk, which is, remember, is going to go this way. We want our domain to the left. Since we have removed z, f of w over w minus z is analytic for w and d epsilon, right? So that, this guy would be singular when w is equal to z, right? But that point is no longer in our domain, right? We've removed it by taking out this circle here. Okay, so now we're analytic here. That allows us to apply Cauchy's theorem. So by Cauchy's theorem, what we have is the integral along the boundary of d epsilon must be equal to z. Sorry, not z, 0. Okay, but we can, since this guy is the union of these two boundaries, we can write this as the integral along the boundary of d minus, because this guy's going in the wrong direction, this guy. And so we find that these two integrals are equivalent to each other. Okay. Try just moving this up. Okay, so the integral along the boundary is equivalent to the integral along the circle of radius epsilon centered at z. Okay, so now let's parameterize this integral over here. We can write w equals z plus epsilon e to the I theta. That's what an arbitrary point on this circle looks like. And so that means that dw will be equal to I epsilon e to the I theta d theta. Then what we have is that 1 over 2 pi I, the integral over the boundary of d. So I've multiplied by 1 over 2 pi I here, is equal to the integral from 0 to 2 pi. So I'm writing the parameterized version of this guy, of f of z plus epsilon e to the I theta d theta over 2 pi. Right, so w minus z is just epsilon e to the I theta, right? So we have an epsilon e to the I theta in the denominator. And then the dw gets transformed into I epsilon e to the I theta. So those cancel, and we just get this factor of I out, which, yeah, I multiplied by 1 over 2 pi I, which is why that I went away. Okay, but remember, so what is this thing? This is our average value of the function integrated over the circle of radius epsilon, right? And we remember that f being analytic implies that f is harmonic, which implies that f has the mean value property. So I said I wasn't sure if we would use this mean value property again, but here we are using it. And this tells us that the integral from 0 to 2 pi of f of z plus epsilon e to the I theta d theta over 2 pi. So this average value of f over the circle is just equal to the value of f at the center. And so at the end of the day, what do we have? We have that 1 over 2 pi I, the integral over the boundary, is in fact equal to f of z. Okay. So that is Cauchy's integral formula, this guy here. And now I don't have time to prove the derivative versions, but you basically just take the derivative of both sides with respect to z, right? And you have to argue about whether things are differentiable or not, but let's ignore that and just write down the equation. The nth derivative of z is equal to m factorial over 2 pi I, the integral over the boundary of d, f of w over w minus z to the m plus 1 dw. So this comes from here by taking the derivative with respect to z on both sides, m times. And we do so, some argument has to be made about whether things are differentiable at each step, but we're going to ignore that. Okay. And then I want to point out that this tells us one important thing. If f is analytic on a domain D, then f is infinitely differentiable. And the successive derivatives, so f prime, f double prime, and so on, are all analytic on D. So this analyticity property is very, very strong. It gives us smoothness of our function, right? And all the derivatives. Okay. And now let me close with just a couple of simple examples. We integrate along the circle of radius 2, z squared over z minus 1 dz. Well, we can evaluate this guy easily. We call this thing our function f, right? And we apply Cauchy's integral formula. This tells me that this should be f of z squared, sorry, f of z evaluated at z equals 1, which is z squared at z equals 1, which is just, sorry, I forgot my 2 pi I. 2 pi I, 2 pi I. And so this should be equal to 2 pi I. Okay. I have a 2 pi I right here. So I've just moved it over to the other side. So another example would be the integral over the curve, which is a circle of radius 2 pi of function z squared sine of z over z minus pi cubed dz. So I recognize this as my function, and I recognize this as m in the derivative version of Cauchy's integral formula. And so m here is, well, sorry, 3 is not m, but m plus 1. So m is equal to 2. And so what we find is that this is equal to 2 pi I over m factorial, the second derivative of z squared sine of z evaluated at z equals pi. And I'll let you work out the details, but this comes out to minus 4 pi squared I. And finally, what do you do when you have a denominator which is of like a mixed form? Suppose you have the integral over the circle of radius 2 of the exponential over z squared times z minus 1. Okay, now we have singularities at 2 points, one at z equals 1, one at z equals 0. So what we can do is, well, here is the circle of radius 2. So let's say this is 0, this is 1, this is 2. And what I can do is I can remove a circle of radius epsilon around 0 and a circle of radius epsilon around 1. All right, so now my boundary is going to look like this guy, and this guy. So this integral is equal to, so when I take my boundary to be, or when I take my domain to be this region with these circles removed, I can apply Cauchy's theorem, right? Because this thing will be analytic in that region because I've removed the singularities. And that'll tell me that the integral over that combined boundary, so over this, this, and this, is equal to 0. And so that tells me that this integral, the one I want, which is this one here, is equal to the integral of radius, the integral over the circle of radius epsilon centered at 0. So I would have gotten a, when I apply Cauchy's integral formula and I move the other integrals to the other side, I would have gotten minus signs, but these guys are being integrated in the wrong direction, so we just flip the directionality here to correct the minus sign. Okay, so now this guy is analytic. Well, okay, so I should say it like this. This guy is analytic in this region, and then, or inside this region rather, and this guy is analytic inside this region. So this will be my f for this integral, and this will be my f for this integral. And now I just apply the Cauchy integral formulas again. And I'll just tell you what you get. So this will be 2 pi I times derivative of e to the z over z minus 1 at z equals 0. And this will be 2 pi I e to the z over z squared at z equals 1. And what you get at the end of the day is 2 pi I e minus 2. Okay. So another approach would have been doing like a partial fraction decomposition here and splitting this into 2 integrals. But this is just as good. Okay. Any questions? Sorry, I went way overboard. I really wanted to do that Fourier transform example. Stop the recording.